Welcome back. In the last segment, we discussed the difference between solid and liquid rockets. For solid rockets, we saw that the propellants, the fuel and the oxidizer, are mixed together and stored as an inert solid. As a more common example of a solid rocket, I discussed fireworks. A firework is a type of solid rocket that you can store for a while and then ignite. For liquid rockets, the propellants are stored separately and then they're mixed just before ignition. When NASA uses liquid rockets, they commonly combine liquid hydrogen, the fuel, and liquid oxygen, the oxidizer. And when these are mixed and ignited, it creates a lot of energy, something you definitely don't want to do at home. But I do want to provide you an example of a liquid rocket that you could do at home with just household items. This is a liquid rocket that combines baking soda and vinegar. And these are the same ingredients for like those infamous school project volcanoes where you pour the baking soda and the vinegar in and paper mache and the whole thing erupts. In both cases, when baking soda and vinegar are mixed, there's a chemical reaction that creates energy, and the exhaust that's produced is carbon dioxide. And we've made a video showing you how to do this, but just be careful and make sure you do this launch outside. NASA doesn't use vinegar and baking soda in their rockets, although it would definitely be cheaper. And while it seems obvious, to really explain why this combination doesn't work as a rocket for NASA, we need to discuss something called the rocket equation. The rocket equation is really cool. It's maybe not my top equation, but it definitely makes the top 3. And we'll talk about it in the next few minutes, and we'll walk through it. So the rocket equation describes the maximum speed a rocket can achieve by burning its own fuel. It's also called the Tsiolkovsky equation after the Soviet physicist who derived it in 1897. Konstantin was also the first person to derive the speed needed for low Earth orbit and to think about staging rockets, which we're going to discuss in the next segment. Tsiolkovsky was inspired by the idea of a boat filled with rocks. So the idea is that if you're on a boat and you want to get moving, you can throw off one of those rocks in the opposite direction and your boat will go forward. And if you throw off a second rock, you'll actually move even faster because your boat is a little bit lighter now. This is similar to rockets. So as the rocket burns its propellants, it moves forward, but at the same time, it's also getting lighter. The rocket equation describes this change in velocity, speed, before and after the rocket fuel is burned. The change in speed is known as delta V. So the triangle thing is the Greek letter delta, and this symbol is used in physics to represent the change in some value. So delta V is the change in velocity. And this is the same quantity we've used previously when discussing how to change orbits. Delta V is so important and discussed so often in rocket science that people have literally named their kids after it, and that's super awesome. Why is the rocket equation interesting? So as we burn rocket fuel, the rocket gets faster, that is, the delta V increases. However, as we burn rocket fuel, the rocket also gets lighter. That means as I burn through my fuel, it's getting easier and easier and easier to push the rocket forward. This is happening in your car. That is, when the gas tank is full, you get slightly worse gas mileage compared to when the tank is empty. But it's so tiny and it's such a small fraction of the total weight that we just don't even notice it. In rockets, this is totally key. So, all right, let's get started. From Newton's third law, we know that if we push exhaust out one end, the object will go in the other direction. From Newton's second law, we know that both the speed and the amount of that exhaust determines how fast the rocket will move. So let's look at this in more detail. Imagine I have some rocket, and that rocket has a mass, we'll call it little m. At first it's at rest, so it's on the launch pad, and the velocity is 0, so v equals 0. At time t equals 0, I ignite a little bit of rocket fuel. Say it has a mass dm, and it leaves the rocket. Now my rocket is slightly lighter, so m minus dm. The original mass of the rocket minus that tiny bit of exhaust mass. That exhaust left the rocket with some velocity, a speed which we're going to call the exhaust velocity, or VE. From Newton's third law, if the exhaust is going in one direction, our rocket's going to head in the other. And the velocity that the rocket gains from this little chunk of rocket fuel will be little dv. This happens over and over again. A small amount of fuel, dm, leaves the rocket with exhaust velocity VE. The rocket gets slightly lighter each time, m minus little dm, and its velocity increases by some amount. And we can add up all of these moments together. We add up all of the little dv's to determine the total delta v. The rocket starts with some initial mass, and we'll have some final mass, which is the final mass is the original mass minus the fuel that it burnt through. With a little bit of math, which we won't do here but is really fun, we can come up with an equation, and this equation is beautiful. The rocket equation says that delta v, the change in velocity of my rocket, is equal to the exhaust velocity, VE, times the natural logarithm, we'll talk about that in a sec, of the initial to final mass. And this little ln thing called the natural logarithm, it's a logarithm. You can ask Google to calculate it for you. So for example, the natural logarithm of 10 is 2.3. And the logarithm comes from integrating a quantity that scales as 1 over x, but it's all good. So coming back to the equation, we can determine the speed of a rocket by taking the natural logarithm of the ratio between the initial and final mass and multiplying by the exhaust velocity. Okay, so first we need to ask, what is the exhaust velocity? The exhaust velocity is completely set by what rocket fuel you've chosen. We can assume that this is a single constant value. So if you chose a solid rocket or a liquid rocket, you can look up the velocity, the exhaust velocity, in a table. And here's a simple version of such a table, so propellant type and exhaust velocity in kilometers a second. For solid rockets, the exhaust velocity is about 2 kilometers a second. For liquid rockets, the exhaust velocity is a little better, about 2.5 kilometers a second. And for the black belts out there, these are effective exhaust velocities when launching from the ground. These values take into account the fact that you're going through the atmosphere and you have to climb up through the gravity of Earth. Once we're out in space, the exhaust velocity values are about 1 kilometer larger. So if we really want to dig deeper into these numbers, the table that I showed in the last segment provides an estimate of the exhaust velocity. That is, the specific impulse is directly related to the exhaust velocity. So liquid hydrogen has a larger exhaust velocity as compared to other liquid rocket combinations or solid rockets. Okay, so now let's use this rocket equation in an example. Let's say we want to get to low Earth orbit, 500 kilometers above the Earth. From our past work, we know that this requires an orbital velocity of more than 7.5 kilometers a second. That is, if we're sitting on the launch pad, we need to increase our speed, a change of delta V, a change of velocity, to at least 7.5 kilometers in order to maintain its orbit. Once we've chosen our rocket type, let's say liquid rocket, the effective exhaust velocity is set at 2.5 kilometers a second. We can use the rocket equation to figure out what the fuel ratio I am allowed for a successful launch. So let's start with the fuel carried by a typical airplane. An airplane before takeoff is 30% fuel and 70% everything else. So the initial to final mass is 100 to 70. Going back to the rocket equation, delta V is equal to my exhaust velocity, 2.5 kilometers a second, times that natural logarithm of 100 over 70. And if I calculate this, the delta V is 0.9 kilometers a second. So this is not even close to the velocity I need to get into low Earth orbit. All right, let's dial up this number. We can't change the exhaust velocity, but we can change that weight ratio. So now let's say 80% of my launch mass is in fuel and 20% is everything else, where everything else is the structure of the fuel tank and my payload. We can plug and chug into that rocket equation again. So 2.5 kilometers a second times the natural logarithm now of 100 over 20, so 100 minus that 80% in fuel, 4 kilometers a second. Darn, okay, we're getting close, but we're not there yet. Let's dial up the weight ratio even more. So now let's say I have 90% of my mass in fuel and 10% is everything else. This is like getting kind of crazy, right? Most of my mass is in fuel, but all right, let's just do it. Again, putting this into the rocket equation, 2.5 kilometers times that natural logarithm of 100 now over 10. That's equal to 6 kilometers a second. So like, seriously, I'm not even gonna get to orbit with 90% of my fuel and my mass in fuel. Okay, we'll dial it up a little more. So 95% of my mass is in fuel. 5% is everything else. So now 2.5 kilometers times that natural logarithm of 100 over 5, that's equal to 7.5 kilometers a second. So gosh, we might finally be getting to orbit. But let's pause for a second. What does 95% of my mass in rocket fuel look like? So for scale, let's look at a soda can. A soda can is a super efficient way to carry soda. In this case, 94% of the mass in a soda can is the soda. And so we need to be slightly more efficient than a soda can when we're carrying our fuel to orbit. So now think of replacing the soda with rocket fuel. My payload is basically like the little tab on the soda can, and we somehow need to make sure that that whole thing is stable enough to withstand a launch into space. Luckily, we have a few tricks that we're going to talk about to improve the situation slightly, but only slightly. These will get us a few more percentage payload back. Okay, so I want to come back to my baking soda rocket. We can now explain why NASA doesn't use vinegar and baking soda for their rockets by looking at the rocket equation. The exhaust velocity for liquid rockets, let's say liquid hydrogen and liquid oxygen, we set is about 2.5 kilometers a second. That value is set by the chemical reaction of the hydrogen and oxygen mixture when it gets ignited. The chemical reaction between baking soda and vinegar creates an exhaust velocity of 0.015 kilometers a second, so 15 meters a second. And if I go back to that exhaust velocity table, baking soda and vinegar is like way, 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 way down there. This exhaust velocity is never going to be enough to get us into orbit, no matter what that weight ratio is. And that's the rocket equation. It's pretty brutal. Taking another look at the equation, we can try and figure out where we might be able to do better, and the bad news is that we just can't change the exhaust velocity given current technology. It's really difficult, and we've pushed that about as far as we can go. The good news is that we can be kind of clever and improve our delta V's by launching rockets in stages, and that's what we're going to focus on in the next segment.